Ready to start? Okay. Welcome back. If you haven't handed in your assignments, or the exercise, please do so at the front of the class. I took a look at the exercises that you did last time, comparing Cuthill-McKee ordering and reverse Cuthill-McKee ordering. I thought the results were very, very interesting. I had never done it myself, but I just guessed that maybe RCM would be better. So it was very interesting to see how much better it was, and to see if anyone found any examples, any matrices for which RCM was worse than Cuthill-McKee. Did anyone find any like that? No. I was a little bit surprised because I'm not exactly sure if it is always true. Right? There's nothing that really says that is always true as far as I know. And I think it could be a very interesting project if you want to choose something like this for the project, to try to understand why RCM is better. And in particular, to maybe come up with another ordering, such as reverse breadth first ordering, and to see if reverse breadth first is comparable to RCM. Right? So we have these matrices. Normally, normally Cuthill-McKee starts at one corner of the mesh, the pseudo-peripheral node, right? And then it expands by levels to the rest of the mesh. So the ordering for Cuthill-McKee often looks a little bit like this, right? If we have a relatively small matrix, it's fairly narrow at the beginning, and when you get to the end, it's fairly wide. Okay? And then when you reverse the ordering in RCM, so this is Cuthill-McKee in RCM, okay? And then it looks just the opposite. Okay? And there could be structures in between. Like maybe there are structures that look like these lower arrowheads and upper arrowheads over here, right? But instead of using RCM, you could use breadth first search, right? So you could use a breadth first ordering, right? It probably also looks something like this, but do you still get the arrowheads? I'm not exactly sure whether the arrowheads come from the level structure between multiple levels, or the levels or the structure within a single level. Okay, so this would be breadth first ordering. And you can think of a brand new ordering. And this is something, again, that I've never done, but I think it could be very interesting for a project. The reverse breadth first ordering. Okay, so it would look something like this. Oops, it looks something like this, and whether or not there's some structures in here, I'm not sure. So now we know that between these two, RCM is better, right? But then now between these two, is RCM always better? I think that could be an interesting question. If you're going to do this project, one thing you might want to do is to write your own breadth first algorithm using C and call it from a next interface. Or you could write a breadth first algorithm in MATLAB. Or you can use, in the latest version of MATLAB, I think 2016B or something like that, maybe 2015B, okay, not that new. There is a breadth first algorithm, right? And in the breadth first algorithm, remember, the ordering within the levels is not really defined. And you would have to randomize that a little bit to see how well it works, right? So this is not a unique ordering. This is probably not unique either, but this is definitely not a unique ordering. And you have to randomize it a little bit to see how well it works. So doing this carefully will, I think, require some thought, and I think could be an interesting project if you're interested in this. Okay? But anyways, thank you for doing that. I thought the results were very interesting to me. I think this result will be very interesting to me as well, and hopefully interesting to you. Okay, so today we're going to start a new topic, and we're going to start talking about preconditioners, which are methods that can be used to accelerate the convergence of iterative methods, such as the conjugate gradient method that you learned in the first part of this course. And incomplete factorization preconditioners are probably the most well-known and the most popular preconditioners when you do not know anything specific about the matrix. So sometimes if you're solving a specific problem, such as a problem from Navier-Stokes, you know something about the physical equations, and from there you can derive a physically based preconditioner. Okay? But if you don't know anything about the problem, meaning someone has just given you a matrix, maybe not even given you the mesh, then there's a preconditioner based on incomplete factorization that works remarkably well. Okay, so we're going to talk about that a little bit, and then later on we're going to talk about how to parallelize these types of preconditioners, how to parallelize the application of these types of preconditioners. Okay, so the idea is that if you're given a sparse matrix A, we're going to compute a sparse lower triangular factor L and a sparse upper triangular factor U, such that A is approximately equal to the product of L and U. Okay? So approximately equal to L and U, L times U. So if we have exactly equals to L times U, that's just Gaussian elimination. That's just LU factorization, right? This is called an incomplete LU factorization, or ILU for short. Okay? And the reason why you might want to do this is for a very, very large problem, let's say for a very large 3D discretization of some problem, right? You know that the fill-in in the exact LU factorization can be very large. So the fill-in and the computational complexity can be really large. It can be so large that you might not be able to do the computation on your computer. Okay, so the idea here is instead of computing the exact factorization, we're going to compute an approximate factorization, okay, and one that is still very sparse. Okay, so we don't have as much, or we could have no fill-in, or we generally not as much fill-in as in the exact factorization. Okay, but since the factorization is not exact, we have to somehow correct it. And one way of correcting the factorization is through using an iterative method, or viewed another way, we use this approximate factorization to accelerate the iterative method. Okay? So let's write down that briefly. Incomplete factorizations can be used as preconditioners to accelerate the convergence of an iterative method for solving a linear system of equations AX equals to B. Okay? I know I used AU equals F before, but I'm going to stick to AX equals to B now. Okay? And one example of an iterative method is the conjugate gradient method. Okay? And to remind you about this concept of preconditioning, I'm going to give you an example of a preconditioned iterative method that is not one of these Krylov subspace methods, these fancy methods which I'll mention more about in a moment. But I think that this example will serve to illustrate a number of important features. So here's an example of a preconditioned iterative method, and it is the preconditioned Richardson method. Okay. So suppose that we have computed an ILU factorization. So it's L times U plus some kind of remainder. Okay? So the remainder is 0 if we have an exact factorization. But because it's an approximate factorization, there's some kind of remainder. Okay? And we're going to substitute this into the equation that we're going to try to solve, AX equals to B. Okay? So that is LU plus RX equals to B, right? I've just substituted in. And I'm going to move one of the terms to the right-hand side. LUX equals B minus, maybe I should write the R term first. And actually, in my notes, and probably this will be better for the signs later on, let's do LU minus R. Okay, so I'm changing the R's to minus R. So now I have RX plus B on the right-hand side. So I moved over R. And now I'm going to move over LU. So X equals LU inverse RX plus LU inverse B. And it's kind of difficult to have a method that has R in it because we don't know what the residual is, right? We know what L and U are, but we don't know what R is. But we can express R in terms of A and LU, right? So let's substitute that. So R is equal to LU minus A. And we can simplify this. Okay, I'm being very detailed and showing all of the steps. And from this equation, we can try to define a method, an iterative method. We have x on both sides. Okay, so we could think of defining a method by calling this x at k plus 1, some approximation at the k plus first step. And this is an approximation at the kth step. So starting with an initial approximation x0, we can use this iteration to come up with a better approximation. So the method looks like this. X k plus 1 is equal to I minus LU inverse A xk plus LU inverse B. Okay? If we define, so you can see that everything on the right-hand side is known. We can compute the left-hand side. If we define a residual at step k as b minus axk, okay, then we can simplify this formula to xk plus 1 equals xk plus LU inverse RK. So the method consists of starting with an initial guess, taking in a number of iterations. Within each iteration, we do two things. We compute the residual, and then we update the current approximation. Okay? And importantly, within each iteration, the main computational steps are to multiply by a sparse matrix A and to solve with the L and U factors. Okay? So this is one very important distinction from direct methods, Gaussian elimination, because there is no fill-in, right? The storage that we need stays the same, right? Because all we need to do is multiply by A. Okay, so this kind of explains why last time I spent so much time talking about sparse matrix data structures, right? We want this operation to be as efficient as possible because we're going to do it over and over again. Okay, so we want an efficient data structure for it. And it's also, this operation multiplying a sparse matrix by a vector can also be parallelized very easily because each component of the vector x can be computed in parallel when you use some kind of row distribution. So there are many ways of doing that. So similarly, we want this operation, the triangular solves with the U factor and with the L factor, to be as efficient as possible.
When we get the A matrix, we usually say, for example, we have a 3D grid, we get the A matrix for that. Now, say I already have a domain decomposition stage. So my A matrix, do I need to save that A matrix and then transform into a proper order for the sparse matrix?
I'm not sure I understand your question. So there's no...
I'm saying that I have the A matrix for every domain, every process. Now, do I save that A matrix and change the A matrix to a sparse form? Because right now my A matrix is not in sparse format, right?
Okay. So depending on your problem, you might have a matrix that is sparse or not. So if it is a sparse matrix, you should definitely store it in sparse format, even if you haven't done domain decomposition, which I'm not sure is related here, right? So your application could deliver A in some form to you that is not a sparse matrix, right? And one thing that I maybe should say is that this multiplication by a sparse matrix could be done by having explicitly a sparse matrix available and doing the multiplication, or it can be done by applying your differential operator, your discrete differential operator, okay, to a vector. And that might mean applying some operations that is equivalent to multiplying by a sparse matrix, but you don't actually have a sparse matrix. Okay? So in that point of view, this is just conceptual. Okay, so let me write down some of the points that I just said. At each iteration, we need to multiply by A. So this is the SPMV that we were talking about last time. And we need to solve with L and U, which we haven't talked about yet, but we will talk about next class. Okay? Now suppose that we have an exact LU factorization. Okay. Then this becomes exactly the correction to x. So we get convergence in one step. Okay. So that sounds like a really good thing, convergence in one step. The bad thing is, of course, it's expensive to compute an exact factorization. Okay. Then we have convergence in one step, but the drawback is obvious. Convergence it's expensive to do that, so it's not practical. This is what we're trying to avoid in the first place. And on the other hand, suppose that we were very lazy and we said that L is equal to U is just equal to the identity matrix, right? So, well, we said we wanted A is approximately equal to LU. Who's to say how accurately we needed that? Okay, let's just be very lazy, choose identity matrix for both. Okay, and if we do this, then we have what I would call the unpreconditioned Richardson method. We have the unpreconditioned Richardson. And how fast does that work? Convergence could be very slow, or we might not even have convergence. Okay? So we have slow or no convergence. I haven't said anything about convergence even if we do use a preconditioned method, but I think that's a topic for another course. Okay? So this is where the art comes in, right? We want to find an approximation to the matrix that is somehow good enough, but somehow cheap enough as well, so that overall this Richardson iteration would converge very quickly. Okay? And besides incomplete factorizations, there are other ways of choosing approximations to A in factorized form or in inverse form, different types of approximations here, which can also be used as preconditioners. So a couple important things to note about IOU factorizations is that ILU factorizations can break down, meaning as you're trying to compute an ILU factorization, typically using a Gaussian elimination type of process, you might encounter a zero pivot, right? And then it will break down. And there are symmetric positive definite versions of this factorization, so incomplete Cholesky factorizations. So if you're given a symmetric positive definite matrix, the exact factorization is called the Cholesky factorization. You can also, from there, define the incomplete version of that. And you know that if the matrix is SPD, the Cholesky factorization always exists, right? But the interesting thing is that the incomplete Cholesky factorization may not exist. Okay, so there are some remedies to that, and we could talk about that if there is time. But that is something to be aware of. If you get a matrix, let's say you download it from Matrix Market, or this is your own problem, and you want to compute an incomplete Cholesky factorization, there is a possibility that the factorization will fail. Okay? So this is an example of a preconditioned Richardson method. Let me say a few things about Krylov subspace methods. It's a very beautiful topic, but unfortunately it's not something that we have time to go into. But for the purposes of maybe some review and also going forward with our first assignment, let me just say some very brief things. Okay, so Krylov subspace methods. So a very brief summary of three methods. So Krylov subspace methods, this is a fancy term that is used to describe a family of methods based on optimizing using Krylov subspaces. Okay? But that is something that you might not need to know. I'm just going to tell you some very basic utilitarian things. So suppose you have a matrix A that is symmetric and positive definite. Okay. Then there is one method that you should always use if this is the case, and that is the conjugate gradient method. This is the method that you learned in the first part of the course. Use the conjugate gradient or CG method. And you use it because it's optimal in a certain sense. Okay? And you wouldn't use something like Richardson, but one of the reasons why I'm showing Richardson is that CG has exactly the same structure. Right? This isn't the iteration for conjugate gradient, but you may remember from the first part of the course, depending on how much detail you did. At each iteration, you need to multiply by A, and if in the preconditioned conjugate gradient method, you need to solve by these Lu factors, or solve with the preconditioner. Okay? So this is very easy. Conjugate gradient method is available in MATLAB. Lots of software packages. If you're using PETC, for instance, it's built in. Okay? So now suppose that A is non-symmetric and maybe even indefinite. Okay? So for symmetric indefinite, there are some other options, but I'm not going to talk about those. Then there are some other options, and I'll just mention two of them. One is called the GMRes method, and that stands for Generalized Minimum Residual Method. Okay. So this method has optimal convergence for non-symmetric problems in a very specific sense related to these Krylov subspaces. Okay? But it does have a drawback, which is that the cost of the method increases as you take more steps. Okay? It's not that we have fill-in or anything like that. Okay? If we've taken 5 steps, right, the cost is going to be related to having to do some computations by considering 5 vectors that we considered earlier. If we've taken 1,000 steps, we're going at each to compute the 1,000th step, we need to consider the 1,000 vectors that have come earlier. In the conjugate gradient method, that doesn't happen. Okay? So, but we have optimal convergence, but the bad part, as I just said, storage and computation increase with number of iterations. Okay. One other option, and it's just the third method that I'll mention besides conjugate gradient and GMRes, is called bi-CG stab. And it's a really good contrast to GMRes. In some sense, it's just the opposite. The convergence here is not optimal. There really can be only one optimal method, right? But the convergence here is not optimal. But it has been designed so that the cost of each step stays the same. Okay? So in the first assignment, which I'll talk about at the end of today's class, you're going to be using bi-CG stab in MATLAB. And I could have asked you, in fact, when I was making up the assignment yesterday, I was thinking, well, I was just going to ask you to use GMRes. GMRes is a little bit harder to use because because since the computation cost increases with the number of iterations, what is normally done is that when the cost becomes too high, you just restart. Okay, maybe after 50 steps, you'll say, well, let's just restart with the current approximation, right? The method is no longer optimal from that point of view, okay? But it means that you have to pick an extra parameter, which is how many steps to do before you restart. And the way that MATLAB reports the number of iterations that were required to obtain convergence is a little bit weird, because it reports the number of times you restarted and then the number of steps you took after the last time you restarted. It's a little bit tricky. So the simplest thing to do, I thought, was to just say by CG stab. And by the way, there are something like, for non-symmetric matrices, there's something like 10 different methods that are viable. For SPD matrices, there's just one. Okay, there's no competitor. But here there's 10 different ones. And there's some very recent ones that people think work better than by CG stab. But this is well established and something that you can try. Okay? And if we have time, hopefully I'll show you how to use these in MATLAB. Okay, so let me go. So this was a little bit of a detour into iterative methods to show you how the preconditioners are used. Right? We're not going to transform any equations. Basically, we're going to use these transformed equations implicitly. Okay, so now I'll go on and talk about how to compute these incomplete factorizations. And as I kind of hinted before, the way you compute these things is to use Gaussian elimination, okay, as if you were trying to compute the exact factorization. But you drop small non-zeros that are small in magnitude, during the factorization. So use Gaussian elimination, but drop, and I'm going to talk now about what I mean by drop, small values computed during the factorization. There are two ways of dropping small values, and I'm going to start with one way, and it's really a family of ways, and this is called threshold-based. So I call it threshold-based ILU. And the other one I'm going to call static pattern ILU. But first about threshold. So here a threshold, I'll call it tau, is used to decide when to retain a non-zero. Okay. So for instance, I'll describe what I think happens in MATLAB. Okay, so MATLAB has a incomplete factorization code. So if we have an entry, a non-zero in the upper triangular factor, I'm going to call it Uij. If that is greater than tau times the norm of the jth row, And using MATLAB notation, I'm going to call, the jth column. Since, remember, MATLAB stores things in CSC format, right? Compressed sparse column format. So all of its algorithms work in columns. At least the sparse algorithms work in columns. So this is the norm of the jth column of A. So times tau. So tau would be chosen to be something like 10 to the minus 3 or something like that, okay, depending on how your problem is scaled. This takes into account how your problem is scaled. So you would keep the element if your entry is larger than that. And in the lower triangular part, we might have something that looks very similar. Again, the jth column of A, but because we're going to, in MATLAB, we use a lower triangular factor that has a unit diagonal. Okay, so we're going to divide here by UJJ. Okay. Here we could divide by LJJ, but LJJ is just 1. Okay, so this is a simple way of computing an incomplete factorization. To be complete, let's just say many other strategies are possible. And if you want to make up your own strategy, that could be an interesting project, and you could even probably publish a paper on it. Okay? If you find that your strategy works well, of course. Okay, so the second, let me do an example first. Let me do an example first of this one. So here's an example sparse matrix, 5 by 5 sparse matrix. Okay. So suppose that we want to create a 0 over here. We're going to add an appropriate multiple of the first column. And that's going to create a non-zero in this location caused by this first non-zero, right? And if this non-zero, this square non-zero, is small, less than this threshold, then I'm just going to drop it. I'm not going to even put it in. Okay? And if it's large, then I'm going to put it in. Notice that later on, I might want to create a non-zero over here. And that's going to require me to add some multiple of the second row, right? And if I had put in a non-zero over here, then this non-zero is going to create yet another non-zero over here. But if I did not put in a non-zero over here because it was small, then this non-zero would never be created. Okay, so this is how this incomplete process creates a factorization that is very sparse. So because non-zeros create non-zeros, right? By dropping non-zeros, you save a lot of work, right? So it's very different from computing the exact factorization and then dropping, because that's what you're trying to avoid in the first place. Okay. So let me talk about now the second method of dropping small values. So the second class of ILU factorizations, I'm going to call it static pattern ILU. So here we're going to choose the set of allowed non-zeros in L and U beforehand, right? In the threshold-based method, we chose the non-zeros that we're going to keep into factorization as we go along. But here, we're going to choose beforehand. Okay? And I'm going to do this by specifying this set S as the set of locations in the matrix Ij such that Lij or Uij can be non-zero. Okay. It's a little bit imprecise because, you know, if you're in the lower triangular part, you can only be non-zero in the lower triangular part. Okay. But you get the idea of what this set S is. And here now, of course, is the question of how do we choose these sets S? So a few notes on this. It may not be easy to choose S, but there are many heuristics. Meaning many ideas that should work well, but we don't really have any kind of proof that they work well. Okay. Usually we choose S just based on the sparsity pattern of the original matrix A, but without taking into account the values of those non-zeros in A. Okay, so this is also a big difference between the static pattern ILU and threshold ILU. Here, the threshold ILU, they take into account these values, but usually we don't take into account values here. So this made me think, while I was writing up these notes, this is another idea for a project. If you can come up with a new way of choosing a pattern beforehand that somehow takes into account the values and see how well that works. One advantage of using static pattern ILU versus threshold is that static pattern ILU, in these factorizations, it's a lot more efficient than to compute than these threshold ones because the data structures are completely static. The data structures don't change. Here the data structures have to change because you're going to insert new non-zeros, and that could be expensive. And also they're a lot easier to parallelize. Threshold ILU is very difficult to parallelize because you don't know what the pattern is going to be. Here you can parallelize by somehow partitioning the problem because you know what the structure of the problem will be beforehand. Okay, so let's write a few of that, write that down a little bit. So usually choose S based on the non-zero positions of A, not the values. And the other thing I said was that due to the use of static data structures, the static pattern ILU methods can be more, these methods can be more, instead of saying can be more, can be, well, I guess can be more efficient to compute. and I would say especially in parallel. Okay? Now I'll give a couple options for how to choose S. Okay. So among the static pattern ILU methods, the easiest way of choosing the sparsity pattern S is something called no-fill ILU, also called ILU 0. Okay. So here, the set S is chosen as the elements, as the positions ij, such that aij is not equal to 0, or I is equal to j. Okay. In other words, we only retain in the Gaussian elimination process non-zeros in L and U that correspond to non-zeros in A. And also, we always retain the diagonal. Okay, so I equals j. And generally for discretizations of PDEs, well, maybe I shouldn't say that because there are, usually we'll have this. If we don't have this, this is necessary to have because we want our factors to be non-singular. Okay, so this is called no-fill. And then the other, well, maybe not the other, but an extension, the generalization in a way, is called ILU K, or level, it's called level ILU, where K is thought of, this parameter K is an integer from 0, so 0, 1, 2, etc., which is called the level. Okay? And let me try, this is a little bit hard to explain, but let me try to explain it this way. So we're going to allow K levels of fill-in. So in Gaussian elimination, non-zero values create other non-zero values, right? So here, this non-zero value created this fill-in. And a fill-in itself can create more fill-in, right? So the fill-in that's created by existing non-zeros in A, we call that level 1 fill-in. And a fill-in that is created by level 1 fill-in, we're going to call level 2 or maybe level 3 fill-in. Okay, so we have these levels of fill-in. And the idea is that these higher level fill-ins are often, for problems coming from differential equations, smaller than those associated with lower level fill-in. Okay, we'll see that in a moment. So we're going to allow K levels of fill-in. And we're going to define a fill-in level for each possible location, ij. Okay? And it's defined recursively. And we're going to start with the initial levels of this location ij as being equal to 0 if aij is not equal to 0 and infinity otherwise. Okay, so this is just the definition at the beginning of the factorization, ij, the level of any ij is going to be 0 if it's already non-zero, if it is non-zero, and infinity otherwise. And then we're going to update what the level is as the factorization goes on. We don't actually do this in practice, meaning we don't actually compute these levels in the factorization, but conceptually, since we want to define these levels in terms of fill-in due to other fill-ins, we're going to update by saying the level of element ij is the minimum between two things, its existing level, and the level of ik plus the level of kj plus 1. Okay? So this is because ij, let's say ij,